What's up, chemistry gurus? Today we'll be explaining electrochemistry on all the major topics such as oxidation states, balancing redox reactions, voltaic cells, cell potentials under standard and non-standard conditions, standard reduction potentials, strengths of oxidizing reducing agents, free energy and its implications in redox reactions, concentration cells, batteries, corrosion, and electrolysis. In order to begin teaching our electrochemistry chapter, we must start by touching on some key points addressed in other chapters, such as oxidation is loss of electrons and reduction is gain of electrons. Redox reactions involve oxidation and reduction processes. Redox reactions are involved in many natural processes, such as the browning of fruit, the rusting of metal, and photosynthesis. And the formal definition of electrochemistry is a study of the relationship between electricity and chemical reactions with both spontaneous and non-spontaneous reactions. Our first major topic is oxidation states and oxidation reduction reactions. Let's begin. Keeping track of the oxidation numbers of elements involved in the reaction and identifying whether oxidation state changes for any elements in the reaction helps you determine whether an oxidation reduction reaction is actually occurring. For some reactions, the oxidation numbers change, but we cannot conclude that any element literally gains or loses electrons. An example of this is the combustion of hydrogen gas. This is a good form of bookkeeping, but you generally should not equate oxidation state with its actual charge. An oxidizing agent gains electrons from another element, and therefore it is reduced. A reducing agent loses electrons to another atom, and it is oxidized.
What up, chemistry gurus? Alright, so today I'm going to be balancing this redox reaction between permanganate and oxalate ions. The first step is we split up the two half reactions. In step 2, we have to balance everything out. The first step is we balance all of the chemicals that do not include oxygen or hydrogen. So we add a 2 here on the CO2 to balance out the carbon. The next step for balancing the reactions is adding water to the permanganate reaction to balance out all of the oxygen. The next step is we add 8 hydrogen ions to the permanganate reaction to balance out the hydrogen put in by the water. The last step to balancing is we add electrons to balance out the charges. In step 3, we multiply each half reaction to cancel out the electrons on either side of the two half reactions. So for the top one, we multiplied by 2, and the bottom one we multiplied by 5. In step 4 and 5, we combined the half reactions and subtracted and got rid of the electrons as they cancel out. So yeah, that's it.
Our next section is about voltaic cells. The energy released in a spontaneous redox reaction can be used to perform electrical work. A voltaic cell is a device where the transfer of electrons that occurs in a spontaneous redox reaction is harnessed through an external pathway rather than directly between the reactants. The solutions must remain electrically neutral in order for the cell to produce a charge. We will now cut to a clip showing a voltaic cell that we created. So here's a voltaic cell that we made in the lab. It involves a solid chunk of zinc and a solid chunk of copper. The solid zinc acts as the anode, and the solid copper acts as the cathode. The zinc is placed in a solution of zinc sulfate, and the copper is placed in a solution of copper sulfate. The zinc is being oxidized and the copper is being reduced in this solution. We have a wire connecting the two electrodes to allow for the transfer of the electrons. In order for this to work, we need to have a salt bridge in between the two solutions. Otherwise, the two solutions will gain a charge and not remain electrically neutral, which is required for a charge to be produced. For our salt bridge, we used just basic sodium chloride or table salt, and we soaked it in parchment paper and linked the two solutions. You could tell that it worked because before we added the salt bridge, no charge was produced, and after we added the salt bridge, there was a charge. Let's begin our next section, cell potential under standard conditions. Electrons flow spontaneously from one electrode to another due to different potential energy. The potential energy of electrons is higher in the anode than in the cathode, so electrons flow toward the more positive electrical potential. The difference in potential per electrical charge between two electrodes is measured in volts. 1 volt is equal to 1 joule over coulomb. The potential difference between the two electrodes is called the cell potential, which is also called the electromotive force, or EMF. The cell potential of any voltaic cell is positive. The magnitude of a cell potential depends on the reaction that occurs at the cathode and anode, the concentrations of reactants and products, and the temperature. The cell potential under standard conditions is referred to as the standard cell potential. In order to calculate cell potential, we must use standard reduction potentials, which is the standard potential at each half cell. The cell potential is the difference between the two half cells. In summary, the standard cell potential equals the standard reduction potential of the cathode minus the standard reduction potential of the anode. It is not possible to measure the standard reduction potential of a half reaction directly, so we have to use a reference half reaction to determine values relative to that reference value. The reference half reaction that is used is the reduction of protons to hydrogen gas under standard conditions, which has a standard reduction potential of 0 volts. We use the standard hydrogen electrode to produce this half reaction. The standard hydrogen electrode consists of platinum wire connected to a piece of platinum foil covered by finely divided platinum that serves as an inert surface for the redox reaction of protons to hydrogen gas. The platinum is in contact with both 1 mole of hydrogen protons and a stream of hydrogen gas at 1 atmosphere. The standard hydrogen electrode can be both the anode and cathode of a reaction. Let's move on to concentration cells. Concentration cells are based on the EMF, or electromotive force, generated because of a difference in concentrations of solutions between the two electrodes. This results in a differing potential energy that allows for the electrons to be passed between the two electrodes. The cell holds a charge until the concentrations are equal, and this is the basis for pH meters and is critical in biological processes. I will now begin to explain batteries and fuel cells, which are the real-life applications of Voltaic cells. A battery is a portable electrochemical power source that often has one or more voltaic cells. Consumer-grade batteries are often single voltaic cells, but higher voltages can be achieved using multiple voltaic cells in a series, and the overall voltage will equal the sum of all batteries in the series. The substances used in the cell determines voltage, and the usable life of the battery is determined by the quantity of these substances. Primary cell batteries cannot be recharged and must be discarded when the voltage drops to zero. Secondary cells can be recharged by an external source. I'll now explain some examples, specific examples of batteries used in our everyday life. Lead acid batteries are 12-volt batteries that are used to start the engine of your car. They consist of 6 voltaic cells, each producing 12 volts. The cathode is lead dioxide and the anode is lead. Both electrodes are immersed in sulfuric acid, and this battery is rechargeable by the alternator in the vehicles. An alkaline battery is one of the most common primary batteries used. The anode is powdered zinc in a gel in contact with potassium hydroxide. The cathode is a mixture of manganese dioxide and graphite that is separated by a porous fabric. Electrolysis reactions are non-spontaneous redox reactions driven by an outside source of electrical energy. Electrolytic cells consist of 2 electrodes, often in a molten salt, but can also be placed in an ionic solution. An external source of energy acts as the electron pump, moving electrons from one electrode to the other. The positive terminal is connected to the anode and the negative terminal is connected to the cathode. When the electrodes are inert, they do not react, but act as surfaces for the redox reactions to occur. Active electrodes are involved in the reaction and also have important implications in real life. Electroplating is an electrolytic reaction that deposits a thin layer of one metal on another to improve looks or resistance to corrosion. This is an example of active electrodes being used. Some quantitative aspects of electrolysis is that for any half reaction, the amount of substance reduced or oxidized in an electrolytic cell is directly proportional to the number of electrons passed into the cell. Charge in the cell is measured in coulombs, and electrons can be thought of as reagents in the electrolysis reaction. Here's an example of an electrolysis reaction occurring in a molten solution. We have chlorine as the anode and sodium as the cathode, and they are both placed in a molten solution of salt. We also have a voltage source, or probably a battery, forcing this redox reaction to occur. In our first electrolysis reaction, we have an anode and a cathode that are stuck into a solution of silver nitrate. Silver is formed at the cathode and oxygen is produced at the anode. We can also see that the color of the solution becomes yellow and more acidic, where the electrons or charge is being passed through the solution from the 2 electrodes.